discuss quantum well lasers, a very important class of lasers, quantum well lasers. I mentioned that most of the lasers today have quantum well structures in their active region because of certain advantages. Just before I proceed, in the last class, that is in lecture 37, I made a small calculation error. I was calculating the quarter wave thickness T is equal to lambda divided by 4n for aluminum arsenide. N I had taken as 3.2, and therefore this was 0.8 divided by 4 into 3.2. Up to this it was right, but this is exactly equal to 625 angstroms. I had written 500 angstroms because what I did was I did this, and then for 1 by 16 it was 1 by 16 is this much, but what I did was 0.8 divided by 16, so I wrote 500. Okay, so please make this correction, everything else is fine. Therefore, the thickness will be slightly different. I just saw that I had made a mistake, so I thought I will correct it. So, quantum well lasers. We have studied most of the essential basics of quantum well lasers. Let me very quickly recall quantum well lasers, what we have already studied. So, quantum well lasers. First, in part 1 lecture 6, if you see part 1 lecture 6, we had discussed in detail the density of states in quantum well structure. Density of states in quantum well structures. What we had seen, I may recall that this was the energy axis and this is rho, the density of states. Then for bulk we had a square root of E dependence, which was like this, and for quantum well structures we had density of states which was like step function. So, this is in the valence band and in the conduction band. 2 points to see here, and that is, this is EC, this is EV. The density of states start up to this axis is density of states. So, what I have plotted here is rho c. So, this is rho c of E and this is rho v of E, that is density of states in the valence band. So, up to this first subband energy, that is EC plus EQ1, just recalling what we had studied, there was no density of states, and therefore, effectively, although this is the band gap of the material, Eg is equal to Ec minus Ev, the effective band gap is from here to here, because before this energy there are no density of states. So, the effective band gap was different in the case of a quantum well structure, and we have seen this value here, the density of states. So, here the value is rho c of E for the first subband was equal to mc divided by pi h cross square into Lz. We had considered Lz as the thickness of the quantum well in the z direction, okay, and this is 2 times and so on. So, this is the density of state, and for the valence band rho v of E is equal to mv, where mv is the effective mass of holes in the valence band to Lz. So, this is the what we have seen. The important point, so if I may rotate this in terms of energy axis. So, because here gain, bandwidth, everything we had plotted h nu along this axis. So, if I rotate this, then the density of states would look like this step function. So, this is the density of state. Now, here it is rho of E, energy versus rho of E, rho nu of E. In fact, this is rho nu of E, rho nu of E, that rho of nu or rho of E is a step function like this. In lecture subsequently, you may recall that in lectures 12 and 13, this is just to indicate to you that we have already discussed almost all the essential physics of quantum well lasers. So, we will directly go to device characteristics. So, lecture 12 and we have discussed about energy states in quantum well structures. Energy states in quantum well structures. What we have seen, a very quick recap, is that the allowed energy values are discretized. Being a potential well, being a quantum well, the allowed energy values for electrons in a quantum well are discretized, and therefore, we have, if you take a quantum well, so this is the quantum well. If this is height is V naught in terms of potential, then there are discrete energy values here. Allowed values are discrete. Similarly, allowed values for holes are also discrete. So, this is for q is equal to 1, q is equal to 2, q dash is equal to 1, q dash equal to 2, and so on. So, this is for the holes and this is for the, and allowed transitions are from here to here or from here to here. The allowed transition selection rules require that allowed transitions are these are the allowed transitions. Further, we had seen that the energy, if I take the upper potential well here for electrons, then if this is V0, this is the energy, allowed energy values versus thickness Lz, thickness of the quantum well structure, then we have energy varying like this. So, what are these? These are the allowed energy values for E1, E1 is this one, E1, the variation of E1 and E2, E1, E2, E3 and so on with Lz. The thickness of the potential well, thickness of the well. This has some very important implications in practical devices. So, the numbers could be typically, this is 50 angstrom, this is 100, this is 150, 150, 200 angstrom, typical numbers. And what could be V0? V0 could be 300 MeV, or I will take an example and show you. This may be about 300 MeV or 0.3 eV, for example, or 0.4 eV, 0.5 eV, that kind of numbers we will get. And what we see is the allowed value, which means if you take the well width as 50 angstrom, then this is the value of E1. Here is the value of E1, and you see that at 50 angstrom the second state is not there, or the potential well supports only one state. So, it is a single mode state. So, this potential well here has only one allowed energy value, and if you change this width, the energy comes down. If you increase the energy comes down, which means this level moves down. So, from an engineer's point of view, what is important is if you change this dimension, the effective band gap changes, because this level starts coming down as I increase the width, this level goes up. So, effective band gap is this, that changes. If the effective band gap changes, then the emission wavelength changes. Although the same material systems are used, by simply changing the width of the quantum well, we can change the emission wavelength. This is a very important result and very important consequences. Its consequences or its applications are very important, because from a material systems point of view, that in a fabrication process, changing the material composition is not easy, because it takes some time for the whole process to reach some steady state. And there, whereas changing the thickness is very easy, because thickness of the layer what I am referring to is, if you are on the substrate, if you are depositing a layer by epitaxy, then changing this thickness is very easy. Simply you have to control the time of deposition, and this can be precisely controlled. In techniques like MBE, we can control the thickness very precisely, correct to one monolayer, one atomic monolayer. But changing the composition, it is not, it is possible, but it is not convenient. Therefore, if you want to change the emission wavelength slightly, the same material system can be used, but little bit variation in the thickness of the quantum band. So, this point I would like to illustrate with the help of an example. A very important laser material combination used is indium gallium arsenide versus indium phosphide substrate. So, this is IN 0.53, gallium 0.47 and arsenic. Why we choose this combination is, this material is lattice matched to indium phosphide. So, it is a lattice matched combination. The band gap Eg of this is approximately 0.74 eV. I want to illustrate this point, and indium phosphide is 1.35 eV, which means in this diagram here, so let me erase and draw the diagram corresponding to this. So, this is indium phosphide, this is indium gallium arsenide. And this is indium phosphide. So, this is indium phosphide, this is 0.74. So, what is the Eg difference? The difference in Eg here is, so delta Eg is equal to 0.61 eV, okay, 0.26 and 35. So, it is 0.61 eV, and we know that delta Ec and delta Ev are approximately 35% here of delta Eg and 65% of delta Eg, which means if you substitute 0.61 and 65, this will be approximately, please verify this, 0.4 eV, and this will be approximately 0.21 eV. What is delta Ec and delta Ev? Please see this. This is delta Ec and this is delta Ev. That is the energy gap difference at the valence band, change in Ec Ev value for the two materials. I had written here 0.3. You can see this is what I had written as 0.3, but you get, in my calculation here it is 0.4. So, that is 0.4. If I take a bulk indium gallium arsenide, that is a double heterostructure, okay. Before I discuss, just want to, I had written the title quantum well laser. What is a quantum well laser? I had written the title quantum well laser. What is quantum well laser? Quantum well laser is a semiconductor laser, is a semiconductor double heterostructure laser, DH laser, where the thickness of the active layer, where the thickness of the active layer is less than or of the order of the de Broglie wavelength of electrons. So, it is a double heterostructure laser. Quantum well laser is a normal semiconductor double heterostructure laser, except that the thickness of the layer is very small. Small, very small is quantified in terms of this relation. So, typically 10 nanometers, 5 nanometers, 50 angstroms to 200 angstroms is the typical thicknesses used, so that there are quantum size effects which lead to discretization of energy levels in this potential well. This forms a potential well, which is the quantum well. Now, when the thickness is of the order of, let us say this is 0.1 micrometer, 0.1 micrometer, that is a normal double heterostructure, 0.1, or this is the width. This is the width of the active region. If you see the layer structures like this, then the double heterostructure is here. This is the active region, followed by a cladding region, and we have discussed this, but just I am recalling, it is several classes before. So, this is the active region. The width that I am referring to is this, which we had called now as D. Earlier when we started the physics, it was LZ. So, LZ is nothing but this D here, and these are the cladding layers. So, the example that I am taking is, this is indium gallium arsenide active layer, and these are indium phosphide. So, the band gaps correspond to these. If the thickness is of the order of 0.1 micron, which means is equal to 1000 angstroms, this is a double heterostructure laser. It is not a quantum well laser, it is a double heterostructure laser, because this is very large. Recall that the de Broglie wavelength is of the order of 100, 200 angstroms, and we are more than that, and therefore, it is a double heterostructure laser, which means allowed levels are continuum, almost continuum of allowed levels here. They are discrete, but they are so close that it is essentially continuum, and therefore, the effective band gap is this. So, this is Eg. The emission wavelength lambda g here is equal to 1.24 divided by Eg, which is equal to 1.24 divided by 0.74. For this example, 0.74 here, and that is equal to, you can check, I think it is 1.67 micrometer, approximately 1.67 micrometer. If you now reduce this from 1000 angstrom to 100 angstrom, all right, let me erase this. So, now I am reducing it to 100 angstrom. This is not exact to scale, but just, so this width now is 100 angstrom. So, it is a quantum well now, and therefore, energy levels are discretized. So, if I look at E1, E1 is here. So, this is E1, and E1 dash is also here, which means the lowest allowed energy is here, lowest energy is here. Typical numbers, we had used some typical numbers, you can calculate some typical numbers, that this delta E here, that is from EC, the difference between EC and E1, this is delta E is equal to EC minus E1 or E1 minus EC, the difference is typically equal to 50 MeV, that is 0.05 eV. Please see that this height is 0.4 eV, this is 0.4 eV. So, the shift that you got E1 is 0.05 eV, typical numbers, so that we have a figure. And here the shift is relatively less, and this delta E is typically about 10 MeV. Why do you think the difference is less? The difference is less because of the effective mass. If you recall, the energy E is equal to EC. So, EQ equal to 1 if I put EC plus EQ. So, here EQ equal to 1, the energy corresponding to Q equal to 1. This is equal to EC plus H cross square K. K is pi by D whole square by 2m. 2mc for conduction band and 2mv for valence band. And mv is mass of holes is much higher usually compared to mass of electrons. Electrons have a much lighter have a lower effective mass compared to this. So, the number is small means this number is large. That is why normally you will see that the energy here are different. So, what is the effective band gap now? Please see here, from here to here it was 0.74. Now 0.05, 0.01 added is 0.74 plus 0.06 equal to 0.80. This is the effective EG, EG effective. When it was bulk, the EG was 0.74. Now the effective EG is 0.80, and therefore, what is the corresponding wavelength? Lambda. Lambda here is equal to 1.24 divided by 0.80 equal to. These are indeed typical numbers used for optical communication. Quantum well lasers which are generally about 100 angstroms in thick. You see the wavelength of emission has come as 1.55 micrometer. Low loss, lowest loss window of optical fiber communication. If you reduce this further to 0.8, let us say I reduce this to 80 angstrom. So, if you reduce it further, the level further goes up here, the level further comes down here. So, the effective EG is now this. From 100 angstrom to 80 angstrom, if you go, this may change from whatever number. So, I am just taking some typical numbers. This may become 80 MeV or 85 MeV, and this may become 15 MeV. I am just taking numbers so that they add nicely. So, this becomes 100 MeV, 100 MeV, and therefore, we had 0.74 plus 100 MeV, that is 0.1. So, EG effective is equal to 0.84, and therefore, lambda G is equal to 1.24 divided by 0.84. I think it is 1.4 something, you can check, maybe about 1.46 I think, please check approximately. So, through this example what I have illustrated is you can change the wavelength from 1.67 to 1.46 or 1.55 to 1.46 by changing from 80 angstroms to 100 angstroms. A very small change can change a lot. This means a lot for optical communication, because in optical communication the C band is 1530 nanometer to 1565 nanometer, that is 1530 to 1565 nanometer is the C band. The conventional band for WDM is here, and this change is only 30 nanometers, but we have got almost 100 nanometer change by changing from 80 to 100. So, the point is I can make all lasers required for WDM by simply changing the well width little bit. Quantum well, each one of them is the same material. So, the material scientist has nothing to do, he does not have to change any process parameters. Everything is there, only deposition time is controlled from 80 angstroms to 85, 90, 95, and you can change the wavelength. This is a very important advantage in technology. So, this we have briefly discussed earlier, that modification of band gap by quantum well structures. So, we come to the typical advantages of quantum well lasers. So, why quantum well lasers? They have relatively low threshold, So, quantum well lasers, lower thresholds, less sensitive to temperature, variation, lower threshold currents. This can be quantified by, if you recall that the character I had introduced a characteristic temperature T0, which is approximately 140 K for gallium arsenide, Fabry-Perot lasers, FP lasers. We have discussed this earlier. This is of the order of 400 K for same gallium arsenide quantum well structures, quantum well lasers. What is this T0? Recall that I of T, I threshold, this was I threshold, I used I small IT. This T is temperature was equal to some I0 of IT of 0 or IT of some reference temperature TR into e to the power minus T minus TR by T0, not plus, minus, plus. So, this is a kind of relation we can write for the threshold current. IT at a given temperature T is equal to IT at a reference temperature into e to the power of T minus TR by T0. TR is the reference temperature. What do I mean by this? If you see this, so let us say this is at 20 degrees centigrade and this is at 40 degrees centigrade. Okay. So, T here, this is T, this is TR. If you know at a reference temperature the threshold, so this is ITR, IT threshold current is this at the reference temperature. I am just illustrating what does this mean. So, this is the threshold current now here for I of IT at T. So, T is equal to 40. In our case, TR is equal to 20 degrees centigrade and T is equal to 40 degrees centigrade. I am taking an example to illustrate what it means. And T0 is the characteristic temperature. A large T0 means e to the power of a smaller number, and therefore, IT will be very close to IT, smaller number, e to the power of 0 is 1. So, IT at T would be equal to IT at reference, means there is no change in temperature if T0 was infinity. Larger the value of T, smaller will be the shift to this side. Do you follow this? So, this is the, for quantum well structures, this is very large. Why is so? There are several reasons. One of the most important reason is that because of discrete energy levels, the electron distribution, the carrier distribution within the quantum well structure is not so sensitive to temperature. If you take a bulk double hetero structure, I am illustrating this. So, plenty of allowed states, continuously plenty of allowed states. At any finite temperature, there are phonons which cause electrons to go up, down and so on. An electron comes down by emission of a phonon, and an electron can go up by absorbing a phonon. Phonon transitions, intraband transitions, phonon transitions. If you draw by this side the quantum well structure, this is not to scale. Let us say there are only two levels or one level. For transition here, transitions are continuous. A small change in temperature changes the carrier distribution. You recall the carrier distribution we had drawn some time back, that N and P distributions like this, distribution of carriers. What we had plotted, if you recall, this axis is energy, this was N of E and this is P of E. The carrier distribution is very sensitive to temperature, because temperature, the phonons can induce transitions and distribution changes rapidly. If the distribution changes, the peaks will change, and therefore the maximum gain positions will change in energy. Whereas in this case, the phonons have to make this transition because they are discrete levels, it is not continuum, and therefore it is much less sensitive. Unless phonons have sufficient energy to get this transition, they cannot cause that transition. In other words, the carrier distribution in quantum wells is much less sensitive to temperature, and consequently the threshold is also much less sensitive to temperature. The second point, so this is in terms of transitions. The second point is in bulk. If the temperature increases, non-radiative transitions increase. In the case of a quantum well structure, the transitions are allowed transitions here. There are very little non-radiative transitions. So, eta I is 1, eta I is relatively large in quantum well structures. Relatively large in quantum well structures, and the eta I is less affected by temperature, again because these are quantum mechanically allowed transitions, discrete allowed transitions. Non-radiative transition has to be a phonon transition, whereas these are quantum mechanically allowed transitions, which means they are radiative transitions, and therefore eta I is also less sensitive to temperature. The combined effect of these 2 points lead to a larger characteristic temperature T0. Yet another feature of quantum well structures is, so I had written low threshold, and second one is less temperature sensitive. I have described first the less temperature sensitive aspect. Low threshold, why do we have low threshold? Low threshold, the first point. Let me now discuss the first point. Why do we have low threshold? if you recall, we had an expression for delta nt is equal to jt into tau divided by E into D, or jt is equal to the transparency current density is equal to delta nt into E into thickness divided by tau. D is the thickness of the quantum well structure. And then if you plot the gain coefficient, jt, and if you see the gain coefficient gamma is equal to alpha a into I by it or j by jt minus 1. J by jt minus 1. In the case of quantum well structures, jt d is very small compared to double heterostructures, and therefore jt is a small number. So, this axis if I show j, then jt for a double heterostructure is here, jt for a dh, then for a quantum well structure it is somewhere here, jt for a quantum well structure. The corresponding gamma is here. So, jt is very small, and therefore, as a function of j, this is the material loss coefficient, and if you see gamma, this is gamma, and gamma is equal to lambda square divided by 8 pi tau into rho of nu into Fg of nu, the Fermi inversion factor. This is the expression for gain coefficient, rho of nu into Fg of nu. Rho of nu here is the density of states, which is a staircase like function. This is a staircase function, and therefore, if you recall the class 23, the lecture 23, we have discussed gain in a quantum well structure. So, gamma versus energy h nu we had plotted. For the bulk, it was, if you recall, for the bulk it was varying like this. Then for the quantum well structure, it was step like, because it was a product of gamma was a product of rho nu and Fg of nu. Rho nu for the bulk case is varying like this, that is e to the power of half, whereas for quantum well structures it was a step function, and this, if you recall, this is Eg, this is Eg plus Eq1, and what is this energy? This energy was EFc minus EFv. Gain coefficient for bulk, this is bulk, and the other one is for quantum. The gamma here, the gain coefficient, if you change jt, okay, let me just one second, how will I bring that? With the gain coefficient here increases linearly, that is with current the gain increases linearly. I wanted to show this, just a minute. So, this is j. So, as j increases, jt is fixed, as j increases, gamma increases linearly. Please see this. This is for the case of at any particular frequency, as j increases, gamma increases linearly. In the case of a quantum well structure, jt is very small, but as j increases, gamma will also increase like a step function. gamma increases like a step function. That happens because of the density of states. Because the density of states varies like this, you will see that gamma varies like this. But the important point is, at a low value of current, we have sufficiently large gain. Please see, the gain is much larger at low currents, and therefore although I wanted to bring in here two concepts, that is, one, confinement factor. We have discussed the confinement factor. It will become clear just in a minute. Confinement factor gamma. With this, we had an expression for threshold IT is equal to IT, or J, you can write for J, into 1 plus alpha r. We have derived this gamma into alpha A. And we had seen that, we have discussed this, that the threshold current comes out to be a minimum at a value which is approximately 0.1 or 0.2 micron, and that is why double heterostructure lasers had a thickness D is equal to 0.2 micron. We have discussed this in detail. Okay, so what I have plotted is thickness D here and IT, threshold current, or JT, any one of them. In the case of a quantum well structure, the D is on this side, because this is about 0.2 micrometer or 0.1 micrometer. The minima comes out around here, whereas in a quantum well structure it is 0.01 micrometer, that is 100 nanometer, 100 angstrom, 10 nanometer. This is 0.1 micrometer, which means 100 nanometer, whereas for the quantum well structure it is further down here. Therefore, we would expect the threshold to go up. But why does this threshold go up? Because of the factor gamma, confinement factor. We have discussed this in detail, that the confinement factor decreases, which means in the double heterostructure here, this is the double heterostructure, the optical mode is like this. This is the active region. This is the active region. The optical mode is in this fashion, it varies like this, which means the fractional energy in the core, gamma is the fractional energy in the core, and typically gamma is 0.8 to 0.9, the fractional energy inside the core, this one, that is the confinement factor gamma. If we reduce this thickness, this will spread further. So, if I reduce this here to a smaller value, this mode will spread like this, which means gamma now reduces. This is gamma now. Gamma typically in a quantum well laser, gamma is of the order of 0.4. Here it was 0.8 to 0.9. This has now reduced because the thickness has reduced, which means those of you who are familiar with the optical waveguides, V decreases, V is equal to 2 pi by lambda into D into square root of n1 square minus n2 square. D decreases means V decreases, the normalized frequency V decreases. If V decreases, the mode spreads out, and therefore the confinement factor decreases. If the confinement factor decreases, the threshold will go up, because in the expression gamma is in the denominator. This is the discussion that we had for double heterostructure lasers. But in the case of quantum wells, although the confinement factor decreases, the gain is very large, and therefore the threshold current is still low. Although gamma decreases, the gain is very large at low currents, and therefore the gain is able to compensate for loss. What is the laser equation? Gain is equal to loss here. Although, and cavity gain gamma times gamma equal to alpha r. This is what we need. Although gain, the confinement factor is small for a quantum well, gain at the same current is much larger for a quantum well, because eta I is very high, and there is one more factor, that is Fg varies rapidly, Fg increases rapidly to 1. This has to be appreciated how this varies. I cannot easily show you, and that is why the gain becomes very high at small currents. And consequently, the net effect is, although we are here, so this is for a double heterostructure BH. For a quantum well, this is not true. Quantum well, even at lower values, we have a low threshold. So, gain at a low current is relatively large, and therefore, the threshold is low. One last point with quantum well lasers is multiple quantum well structures, MQW structures. This is the last point I want to discuss for quantum well lasers. The active region of a general laser today comprises of MQW. This is the active region, and this is the cladding region of any laser. I have drawn this diagram many times. This active region, if I zoom, today it comprises of MQW structure, that means multiple quantum well structure. MQW structure comprises of wells and barriers, potential wells and barriers. So, these are the active regions. So, if I draw the band diagram, it will be wells, barriers, well, identical, all of them identical. So, this is for the valence band, and exactly similarly for the conduction band, and this is for the valence band. I hope you appreciate that I have just rotated that band diagram, energy band diagram. So, this is Eg, this is E versus depth, x or d, whatever. Current flows like this. As you know, there is a contact here. This is a longitudinal cross section of a typical laser diode. Current flows like this. So, these are the current strips. So, current is flowing in this direction, which means current is flowing across this. These are the quantum wells and these are the barriers. In an MQW structure, the barrier thickness is sufficiently large so that the electron wave function does not interact, they are isolated. What I have now plotted is not optical mode, please remember this is electron wave function. This is electron wave function. Whenever you have doubt, you just rotate this. In a potential well, so if I rotate this, this is the allowed energy level, and where is the electron wave function? So, this is the electron wave function, fundamental electron wave function, okay, E1 energy. So, this is E1 and this is psi 1, the wave function. So, that is what I have plotted. If the barriers are sufficiently apart, sufficiently wide, then there is no interaction between the wells, and this is called a quantum well structure. A multiple quantum well structure, an MQW structure comprises of several quantum wells which are identical but non-interacting, identical wells. Why do we use this? If I had drawn just one well here, one well, the optical mode I had shown you is this, and I said that it is 0.4, confinement factor is very poor. because the optical mode is wide. If I draw on the same diagram, please appreciate this. The optical mode here would look like this. This is optical mode of the first one. Optical mode of the second one would look like this. Optical mode of the third would look like this, and optical mode. So, what is the point? The point is the optical field, optical mode, EM wave, this is electron function, this is the EM wave field. They are overlapping so strongly that this leads to the formation of a single optical wave like this. Single optical field. The wells are interacting so strongly as far as optical field is concerned. As far as the electron field is concerned, they are isolated. But the it is like two directional couplers. If you take a directional coupler, there is a mode here and there is a mode here. The tails interact and you have a symmetric mode which is like this, one field, symmetric mode. But if you bring this closer, if you bring this further closer, the mode will do this little bit and then like this. And if you bring further closer the two, it will simply become one. You have two waveguides, but they are so close that it will see it as one structure. That is what I am showing here. You have multiple quantum well structure, where as far as the electron is concerned they are isolated, but whereas for the optical field it treats it as one. What is the advantage? You make use of all properties of a quantum well structure and enhance the gamma. Now what is gamma? You see here also it is in the gain region, here also it is in the gain region. So gamma will increase for this effective field, and two, you can get more power from this multiple quantum well structure. If you take one quantum well, the dimension is so small that the power that you would get is limited. But in an MQW structure, there are several active regions which are contributing to the optical power generated, and consequently higher output power can be obtained. So, two advantages of an MQW structure: one, enhancement of effective gamma by having one single optical field, and two, to achieve higher optical power outputs, because overall active area is now much more. If you had only one well, this is the only active volume of the semiconductor is very, very small. But now you can increase the volume by taking 4, 5, 6, typically 3 to 6 wells are used in the active layer of a standard double heterostructure laser. Less temperature sensitive is a good property of quantum well you are making use. Lower threshold, you are making use of that property, and yet you are enhancing gamma and a higher output power. I will stop here for quantum well structures. There are several books on quantum well structures, lot of study on quantum well structures. It is just to motivate that you go through this literature if you are interested. We come to a very quick quiz. Has to be answered in 1 minute. Okay? Very, very simple. One sentence answer, 1 minute. Please focus only on your answer. Please write your name and keep it ready. Okay, there is the question. I have covered because I have written the answer also below. So, answer the following question in 1 or 2 sentences. Why are the end facets of a DFB laser chip provided with anti-reflection coating. Why are the end facets of a end facets means end face of a DFB laser chip are provided with, the end face are coated with anti-reflection coatings. So, why are the end facets coated? Answer in one sentence, maximum two. The end faces of a DFB laser are always coated with anti-reflection coatings, AR coatings. Why? Do not write a big paragraph, that is why I have said answer in one sentence. It should not take more than 1 minute to write one sentence. So, those of you who have finished, please give me. You have to give now 10 seconds. Okay, you have to give now. So, the question is, I repeat, why are the end facets of a DFB laser chip provided with AR coatings, anti-reflection coatings? The answer is, here is the answer, to prevent reflections from the end facets that could lead to the formation of Fabry-Perot cavity or resonances. It is very clear that AR coating, as the name indicates, it is an anti-reflection coating to block reflections coming from the ends. If the reflections come from the end, there will be feedback from the ends and the cavity will also form a Fabry-Perot cavity, and therefore, there will be allowed resonances at those frequencies. To avoid this and to select only one frequency that is selected by the grating, we need anti-reflection coatings at the ends. That is the answer. I hope it is clear.